All right, so what we're going to do now is the crystallization of this particular substance. You don't really need to know what it is because we're only talking about the procedure and the method or the techniques for crystallizing. But it is caffeine, and we have, just for the sake of calculations at the end, I want you to determine the percent recovery. So we have 508 milligrams right now, so 0.508 grams. And then what we wanted to do in the end is determine how much we have after recrystallization has occurred to see if there's any loss of product, which oftentimes there is. And so we want to see how much, right? So we're going to calculate the percent recovery. Now, for crystallization, basically, there's actually a lot of different ways to do this. One of the more common ways that we do it in our lab is by just dissolving it in the minimal amount of hot solvent. Okay, so what is this thing soluble in? That's going to allow for crystallization to occur. Oftentimes, since these are known procedures, there's a lot of there's already a lot of methodologies out there, or procedures outlining it for us. And so for caffeine in particular, I'm going to use ethanol. So here's ethanol right here. 200 proof means that it's 100% ethanol. So basically, and the key here was, remember, we want to dissolve it in the minimal amount of hot solvent. Okay, so remember, solid materials tend to be more soluble in hot solvents, right? And so if we dissolve it in hot solvent, as it cools down, the solubility of that substance will decrease in that cooler solvent, right? And so let's say we dissolved a gram of caffeine inside X amount of solvent, hot solvent, as it cools down, it's not going to have that same ratio of solubility, and so it's going to either precipitate out, meaning form a solid, or it's going to form some nice crystals. If we let that cooling process occur as slow as possible, then we're going to get crystals. Okay, and so I want to point out again, since we are doing this recrystallization process in hot solvent, we have to put it on a hot plate. And since we're working with ethanol, this is fine to be working with on the benchtop. And but we don't want to place this lovely 508 milligrams of caffeine on the hot plate right away. What we want to do is I did the process already, and so I determined personally that I like about 15 milliliters to start with this amount of caffeine. And so I measured out 15 milliliters, and this would be something that might be in the procedure already. If it's an unknown compound and you're trying to recrystallize it, what you want to do is just add a little bit of solvent, so where it's all trial and error, right? So we're scientists, it's all trial and error. You want to add solvent to the solid material before you put it on the hot plate. The reason why you do this is because you don't want to basically burn your substance. You don't want to melt your substance, because once you melt your substance, something called oiling out will occur, and it's just going to ruin the recrystallization process, and you're going to get like a poopy brown oil on the bottom, for example, and it's never going to form nice crystals. You're not going to purify your substance, and you're going to be really upset, right? Because you're trying to get lovely crystals of caffeine. And so that's why you want to make sure you add solvents to your solid material before you start heating it. Now, what I've done here is I have it in a flask, so that way if it gets hot, I can use a nice test tube clamp to go ahead and lift that off. But this isn't going to get so hot that I won't actually be able to grab it with my hand. But that's something you need to be aware of. Know what you're working with, how hot this is going to get, and then make sure you have this proper safety precautions to make sure that you can take care of it safely, right? And so this is just I'm gonna constantly stir this. Again, if you let it sit there, it can heat the solid material on the bottom and then cause that oil that we don't want to have and oil out. Okay, so we have to be constantly stirring this. You can also throw a stir bar in here and then turn on the magnet here to have it stirring. And that stir bar is gonna create a nucleation site for crystals to form on, but then you gotta scrape it off of the stir plate or the stir bar, and it's just a whole thing, right? So I find it very easy to just kind of stir it like this. Now I didn't add that full 15 milliliters because I wanted to make sure that I didn't add too much, okay? This was just an approximation that I made for myself. You want to add, again, the minimal amount of hot solvents to this. Once it starts boiling, then it's not going to get any hotter than that, right? This is ethanol, so it's like 85 or something like that. And that's going to be as hot as it can get. So once it starts boiling, if you find that not all the material is dissolved, what you can do is actually have one of these guys on here as well, and then I'll be stirring both of these at the same time. And then I also have my medicine dropper, okay? And this medicine dropper is gonna allow me to take a little bit of this hot solvent that's just ethanol and place it inside of the recrystallization flask, okay? So you can see that a lot of this material is dissolved. However, here, let me see if I can get you a nice contrast. There's a little glare, but there is still a little bit of material in there. So I'm gonna go ahead and keep stirring this, and this is definitely something you just have to be patient with. And once it's all dissolved, then what we're going to do is take that off the hot plate, place it on our workbench, and then let it sit there for just a few minutes. Depending on the substance, it could take 10 to 15 minutes to crystallize completely, or I do personally know that caffeine will crystallize very quickly in ethanol, and so it won't take much time at all. But the key here is once it's all dissolved, set it aside and leave it alone. The slower and the undisturbed crystallization processes are always going to be the best, and they're going to allow for the best purification of your substance through this method, okay? And so let's see, we're almost there. It's so close. It's so close. You can see just a little bit there. And so we're going to be patient, and we are constantly stirring, okay? So when you're letting it sit there, obviously the good lab techniques or kind of skills are going to be clean up while it's waiting. It's sitting there. Don't just sit there on your and then stare at it. It's like watching water boil. You don't want to do that. A watch pot never boils, right? And so what you want to do is while that's cooling off to room temperature, you want to go do other things. And what we're going to do is actually set up a filtration apparatus. So that way we can do a vacuum filtration to isolate the lovely caffeine crystals that we've obtained. And so then that will allow it to dry as well, because it's a vacuum filtration. It will remove all of the ethanol after 5 to 10 minutes, and then we can weigh it and see how much we've got. I didn't show you the weighing out of this material because that's kind of lame, but I will give you that final number in the end. Okay, and again, we started with 508 milligrams. I see some chunks in here, and those guys are giving me some problems. So what I'm going to do is go ahead and try and smash them up a little bit with something. You can have a glass stirring rod, or you can use. All right, now I'm just using the pipette for the medicine dropper because I can. Okay, so you really can't see that, but just imagine some solid in there, like little chunks, little pebbles almost, and all I'm trying to do is make sure they go away. Because they are, everything else is pretty much dissolved with the exception of just a few crystals. And in a, not to bombard you with a ton of information, but in a laboratory, if I had some stubborn material that really just didn't want to didn't want to dissolve, what I could do is filter that off, because maybe that's not actually caffeine, maybe that's some other impurity that's in here, and I don't want it in there. And so I could also always filter that off really quick and then continue with the recrystallization process afterwards, just to ensure that I get the purest possible sample. So this is why I want you to get these medicine droppers. If I had to, I could, if I kind of observed and realized there's a lot of caffeine sample in here and I don't think any of that's going to dissolve, I would add a little bit, I would pipette carefully a little bit of ethanol into here, and then I would, using a pipette allows me to be more careful and add just the minimal amount, because again, we want only the minimal amount of ethanol to dissolve this caffeine, because that's going to almost ensure that we have a saturated solution of caffeine in hot ethanol. And if it's saturated in hot ethanol, as it cools, a lot of that caffeine is going to precipitate out or form crystals. And so now that we've got it all dissolved, I'm going to go ahead and place it on the bench. Okay, I'm going to go ahead and turn the heat off. And so actually, you know what? In looking more closely at this, there is actually a little bit left in here. So this is perfect because now I get to use my pipette and I will transfer. I'm actually just going to do like a couple drops. So like 1, 2, 3, 4, 5, 6, 7, 8. Why not 8? I like 8. 8's a good number, right? Let's do 8 drops. Why not? So I really feel like that's all we really need. Sometimes you could even add less than that. It just really depends on how much sample you're working with. We're working with 500 milligrams, which is quite a bit. And so 8 drops is totally fine. And we are looking pretty good. Let me get this boiling again. There we go. I think all of it's gone. So now I can place it on the bench top and let that cool to room temperature, and I'll give you a look at it right now. All right, so here it is, looking good. So again, basically you can cover this if you want, or I would just put it somewhere safe, depending on what it is. You don't want your lab mate to knock it over. You don't want to knock it over. You don't want to hate yourself or your lab mate, because that's not cool. Nothing but love, right? But if you let it sit here, cool down to room temperature, nothing happens. What you can also do is add it to an ice bath. Just set it on ice carefully so it doesn't fall as the ice melts. And then after that, if it doesn't form crystals, then what you can do is grab a glass stirring rod. And so this guy right here. And then you scratch at the bottom like that. It's pretty much like this. So once you scratch at the bottom like that, you're scratching the glass. And this is actually just kind of creating an imperfection in the glass that allows for it's basically creating something called a nucleation site. And a nucleation site is just like an imperfection in the glass, or like a porous portion in the glass that allows the solid caffeine material to start crystallizing on. So like it adheres to it, probably intermolecular forces, and then once it sticks to it, another caffeine molecule will stick to itself, and then we get stacks on stacks on stacks of caffeine molecules to make these beautiful needles right before our eyes. Oh my goodness. Have you ever seen such a glorious thing? Such cool needles. Not everything crystallizes in needle form. Obviously, like if you've seen salt, it forms a certain shape, and sugar will probably form a certain shape. Water forms a certain shape, and so it just depends on the type of material. But needles are definitely a common thing for organic materials. Ooh, look at that. That's so cool. Love crystallization. I love just watching it. Sometimes you can see them just grow right before your eyes if you're looking more closely. But that nucleation site, once it's formed and you form a tiny crystal, that's all you need to make it pop off, basically, to form something that we're looking at, like right here. And you can also add like a tiny crystal to a solution that you're trying to crystallize. If scratching it didn't work, a tiny crystal can act as a nucleation site as well. Okay, so like if I had one of these needles and one of my lab mates was struggling to get theirs to crystallize, I can add a tiny needle to their sample, and it might help serve as that nucleation site for more caffeine to crystallize. Okay, so now I've let this sit for quite some time now, and you can tell there's a lot of solid in there. Actually, mostly solid, not very much liquid is obvious, so that's cool. Now what we want to do is go ahead and filter off that solid material and then isolate the nice, pure, crystalline caffeine. And so the setup that we want to use for that is a vacuum filtration. So what I have here is a lab stand, and then we have this, basically, let me take it off for you. It's a clamp. So this is one of the types of clamps that we have in the lab, and it's got this, we basically screw it on to this pole, and it basically holds everything in securely so that it doesn't fall. Now what we've also got is a vacuum flask. It looks like an Erlenmeyer flask, except it's got this little arm and this little like bumps right here are usually going to be where you want to put a vacuum hose. Okay, what does a vacuum hose look like? It looks like this. It's different than a water hose in that it's really rigid rubber, and so it won't collapse on itself when you pull a vacuum. Okay, imagine like sometimes even when you're sucking through a straw and you have this delicious milkshake and it's plugging the bottom, and sometimes when you suck on the straw goes like that. That wouldn't be a very good vacuum tube, right? So what we're going to do is put this on here. We're going to clamp it so that way it's secure and will not fall over. And we want to do this before we connect the vacuum. Okay, hopefully. Oh no, this doesn't work. Oh no. Pause. Okay, so that's a common thing. There's a couple vacuums in this organic chemistry lab that don't work. And so, hey, I just showed you a realistic scenario, right? So move on to the next spot, either in a hood or an adjacent spot. We've got this vacuum tube, and you don't want to connect it until after you've clamped this vacuum flask, because these vacuum tubes, since they're so rigid, they have a mind of their own, and they just go like this, and then they take your flask and they go boom, and they smash it onto the lab bench, and then you broke your glassware, and you're super bummed because now you got to pay for that, and everybody's sad because there's glass everywhere too, so we don't want to hurt ourselves. Anyway, and now we've got this neoprene adapter. This is the smaller one of the two. The way to know which one you use is basically if it falls inside, that's too small. And it's going to be really hard to get out, so be careful when you do that. But this one sits right on top. You can barely see the lip. Kind of chilling right there, yeah? Boom. And this right here is called a Buchner funnel. Remember that was like, it's the one that kind of, I think I said it looks like a box. It's got the square top, and then it's got the holes right there. You put a nice little circular filter paper in there, and it sits amazingly on top. And then you go ahead and put that on there, and voila, we've set up our vacuum apparatus, our filtration device. And then if we pull our vacuum, you can hear it sucking. Okay, first thing you want to do before you add your material to it is wet the filter paper with a little bit of the solvent that you used, so that way it sucks it down, because right now the filter paper is kind of ripply, and it's possible that when you pour it over, some of the solution that you pour in can sneak underneath, and then solid can fall down into the vacuum flask, and then we'll lose material that'll decrease our yield, and we'll be super bummed because we didn't get 100%, which we're probably not going to get anyway. But either way, we want to maximize our yield, right? And so that's one of the ways that we can do that. Another thing I want to mention is if we're doing something like crystallizing sugar at home or salt, you're not going to really have the same setup, right? And so what you can do is, I'm just going to do this very carefully. You can see the clear liquid right here, right? And so what we're going to do is I'm just going to pour that off. And this is called decanting. So when I say decant a solution, I mean pour off the liquid, but leave the solid behind, okay? And so this is something that you can easily do at home to kind of separate your solid material from your liquid material. You're going to have to be careful because it's not always going to be stuck at the bottom like it was for caffeine. I just made for an easy example of decanting for me. Perfect. I totally planned that, by the way. But now I'm going to take my glass stirring rod, or whatever I have, and I'm going to break up that solid material, and I'm going to pour the rest of it, okay? So I'm going to turn this vacuum on. I basically wet it already, and so now all of the filter paper is kind of suctioned to the Buchner funnel, B-U-C-H-N-E-R, and now I can go ahead and pour it off very quickly. You can see stuff going down, and then I still have more in here. If you want to go ahead, I'm not going to, but if you wanted to rinse your caffeine to maybe get the rest of it out of this particular flask right here, you don't want to rinse with just regular old ethanol because it is soluble in ethanol, right, to some degree. And so what we want to do is actually rinse it with cold ethanol because, as we know, caffeine is less soluble in cooler ethanol. And so this will prevent any significant loss by dissolving it, but we can still get more of the material out. And check it out. There's a good amount of caffeine stuck in here. And so it might be a good idea to rinse that in another scenario. But really all I want you to kind of gather from this is the process of recrystallization. And then, I mean, you saw me pour it off. Now I'm going to let this hang out here for about 5 to 10 minutes. And what we're going to do is take a look at the final mass to determine how much we obtained from that 508 milligrams that we started with, okay? And so this will give us an explanation as to why certain procedures or chemical reactions aren't going to yield 100%. So one of the things obviously would be that maybe the reaction didn't go to completion, or in the case of caffeine, we might extract it from tea or coffee, but maybe our extraction procedure wasn't very good. And then also when we finally purified it, we obviously have some white material down here, we left some here, and so we lost product like that. But I'm going to show you this. It looks really cool in there. So let's take a look at that.
Look at that. I love the way it looks. It kind of reminds me of a truffula tree. I don't know if my kids are really into the Lorax, and they smell like butterfly milk or something, and they feel like silk. The truffula tree. So it looks so soft and like fluffy. You can make a knead out of it. I think it would be amazing. And but also when you're looking at your material anyway, right? It's always best to kind of spread the material out so that way we can make sure that we can get the ethanol kind of sucked out of the material as best and efficiently as possible. And so that's going to be done by kind of spreading it out so that way it comes in contact with the filtration or like the filter paper. That way the vacuum's actually having an effect on it. And so
that's pretty much it for the filter or the recrystallization process. So what I really want, I'll give you that number for the final mass in just a second. But what I really want you guys to do is do this at home with either sugar or salt. Or if you're feeling ambitious, I would really love to see you guys do both. Now, obviously, you're not going to be able to um, do this like kind of like the way I did, but so instead of ethanol and caffeine, you're going to be using water and sugar, or water and salt, and you're going to have to do it on the stove. And so I guess technically you could probably do it with a microwave if you didn't have a stove. Um, Although that procedure would probably be pretty tedious, but I think it's really important to learn how to do this stuff. Like if you did have that stove, to add the minimal amount of water to your sugar or salt material to dissolve it, but in hot water. Okay, and so when we do this, we need to be really careful because hot water is what is it? Hot, so it can burn you. And I want you guys to be really careful with this. But I mean, it's just water, right? So hopefully you guys know how to like cook pasta, because that's all it'd be the equivalent, right? We're boiling water. But add the minimal amount of hot water to the sugar or salt to dissolve it. Sugar and salt are really soluble in water. So for example, sugar is, I think you can do a 1 to 3 ratio, and that is 1 cup of water for 3 cups of sugar. That's a lot. I'm not expecting you to use all of that, but what we want to do is make some rock candy. And so I'm going to create my own video, but I'm not going to really put too much dialogue to it. I'm just going to show you the process, and then we will see the outcome, right? I'm going to make rock candy. It's going to be super awesome. And I want you guys to do sugar and salt to see how the crystals look different, okay? I think this would be really cool to observe, and because the crystal lattice that's formed is obviously going to be very different, because sugar is this cyclic, basically carbon, oxygen, and hydrogen containing compound, while salt is just sodium and chloride. And it's just the two things kind of just chilling next to each other, and then they form this really awesome structure in the solid form. And so I think it would be really cool for us to kind of observe that. Okay, so let's take a look at the mass of this final product of caffeine. Hello there. So basically, I scraped off this material, the caffeine from the Buchner funnel, onto this whey paper, and what we've got is 0.377 grams of caffeine on there. And so you may or may not be able to see. Let's see. I don't know how to affect the light here. Let's see. Tap the screen. There you go. So maybe that you can see it or not, but there's a little bit of caffeine on that Buchner funnel, and so there's some loss there, right? So that's just another thing that we have to deal with when we are kind of transferring materials from one vessel to the next. Now, one thing I want to mention is, if we wanted to maximize our yield, I can just take some ethanol, dissolve it in here, go back to that vacuum flask, dissolve whatever's in there, or whatever was left in the recrystallization flask. I can go and recapture all of that material, dissolve it in ethanol, and then recrystallize it again to maximize my yield. So keep in mind, the stuff that went through the Buchner funnel, that was in solution, right? And so the recrystallization process is a purification process. And so the stuff that went through the flask, or the Buchner funnel filter, that stuff is going to be less pure than this stuff right here. So I don't want to combine it, even if it was just solid material. Recrystallizing it again is totally okay, but keep in mind that this is probably going to be the purest and largest batch of material that I can get out of it. Any subsequent recrystallization is going to obviously yield less material, because we have 373 milligrams of it right here, and so there's only about like 130 milligrams in kind of scattered throughout the different vessels that we've transferred it to. And so crystallizing 100 milligrams is a lot harder, or requires less material, less ethanol to recrystallize that, and so it's just going to yield. Maybe we'll get like 50 milligrams out of it, and so sometimes it's worth it, sometimes it's not. Just depends on the material that you're working with and your goal. If it was something that you spent like 6 months making, and now it's like going to cure cancer or something, then you might want to go back and recrystallize that again to get the most out of this whole process, right? So it's just gonna depend, right? Or what you can do, if this something that you do all the time, well, let's say you did this reaction, let's say like 5 times a month. Well, if I combine all of this stuff with the other stuff after the 5 reactions, that's another 500 milligrams, right? And so I can combine all of those into one batch and then do a recrystallization at the end of the month, and then boom, I got another 370 milligrams, right? Or 373, whatever it is. Okay, and so this is just me telling you how to be super awesome in a lab and be very efficient. Atom economy is really important, as well as yields, and so we got to figure out how to maximize our yields in any way, right? And sometimes recrystallization process, for example, is going to give you less than you started with because that's the nature of it, and that's just something you got to deal with. So sometimes it's okay. Sometimes you can figure out ways to improve that yield. So again, I would show you, but the scale is actually, as I messed with it, I'm touching the table, it's going back down. So again, let's just call it 373 milligrams, so 0.373, okay? And then, so what you want to do is that number divided by 508 times 100%, and that's going to give you your percent recovery, okay? Okay, bye.
Sweet smell of butterfly milk. Oh, everybody now, na 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 na. Hey guys, come on. Where's my backup chorus?
All right. Hopefully you enjoyed that. Let me know if you have any questions. Bye.